Hello everyone. Today we will study sequence. First of all, let me introduce what is a sequence. A sequence is a list of real numbers. It may be finite, it may be infinite. And it may or may not have patterns. A sequence is a list of real numbers. It may be finite, it may be infinite. It may or may not have patterns. Let me show you some example of sequence first of all. For example, 2, 4, 6, 8, 10. This is a finite sequence. This is a finite sequence. This sequence is finite. It's called finite sequence. Here we say the first term is 2. So we say a sub 1 is 2. A sub 2 is 4. Second term is 4. A sub 3 is 6. The third term is 6. A sub 4 is 8. The fourth term is 8. A sub 5 is 10. So that's an example of a finite sequence. Another example, a sequence may look like this: 7, 9, 1, 2, 3, 11, 10, and so on. This is an infinite sequence and it has no patterns. In the sequence, A1 equal to 7, A2 equal to 9, A3 equal to 1, and so on. Note, more generally, we can treat sequence as function from the subset of integer to the set of real numbers. We can treat a sequence as a function. From a subset of integers. To the set of real numbers. For example, in example 1, we can write A1 equal to 2, A of 2 equal to 4, A of 3 equal to 6, and so on. In example 2, we can write a1 equal to 7, a2 equal to 9, a3 equal to 1, and so on. So in general, we can treat a sequence as a function from the subset of integer to the set of real numbers. Since we can treat a sequence as a function, then sometimes when a sequence has patterns, we can use a formula to express a sequence. For example, for each of the following sequence, list the first 5 terms. First sequence, an equal to 2n plus 3, where n is greater or equal to 1. List the first 5 terms. So first term, a sub 1. For a sub 1, I plug in 1 for n. I get 2 times 1 plus 3, which is 5. A sub 2 is 2 times 2 plus 3, which is 7. A sub 3 is 2 times 3 plus 3, which is 9. A sub 4 is 2 times 4 plus 3, which is 11. A sub 5 is 2 times 5 plus 3, that's 13. So if I list the first 5 terms of the sequence, it looks like this: 5, 7, 9, 11, 13, and so on. That's the first 5 terms of the sequence. We can see that it has a pattern here. Next example, a sub n equal to n squared plus 2, where n is greater or equal to 0. The first 5 terms, since I start from 0, my first term is a sub 0. That's 0 squared plus 2 equal to 2. A sub 1 is 1 squared plus 2. That's 3. A sub 2 is 2 squared plus 2, which is 6. A sub 3 equal to 3 squared plus 2 equal to 11. A sub 4 equal to 4 squared plus 2 equal to 18. So the first 5 terms of the sequence, since I start from 0, the first 5 terms is A0, A1, A2, A3, A4. So the first 5 terms of the sequence is 2, 3, 6, 11, 18, and so on. Next. A sub 1 equal to 2, and a sub n equal to 2 times a sub m minus 1 plus 1, for n is greater than or equal to 2. List the first 5 terms. We know that a1 is 2. How do we find a2? For n is greater or equal to 2, we plug in 2 into this formula. If I plug in 2 for n, I get 2 times a sub 2 minus 1 is 1. I get 2 times a sub 1 plus 1. So if I plug in a1, a1 is 2. 2 times 2 plus 1 is 5. Next term is a sub 3. For a sub 3, I plug in 3 for n. I get 2 times a sub 3 minus 1 is 2. I get a sub 2 plus 1. A sub 2 is 5. 2 times 5 plus 1 is 11. Next, a sub 4. I plug in 4 for n. I get 2 times a sub 4 minus 1 is 3. A sub 3 is 11. 2 times 11 is 22. 22 plus 1 is 23. A sub 5 is 2 times a sub 4 plus 1. A sub 4 is 23. 2 times 23 plus 1 is 47. So the first 5 terms of the sequence is 2, 5, 11, 23, 47. That's the first 5 terms of the sequence. In this formula, refer to an. A sub n minus 1 represents the previous term. So every term is 2 times the previous term plus 1. In this formula, every term is 2 times the previous term plus 1. Every term is 2 times the previous term plus 1. Every term here is 2 times the previous term plus 1. 2 times the previous term plus 1. Every term is 2 times the previous term plus 1. Next example. A sub 0 is 2. A sub 1 is 3. And a sub n equal to 2 times a sub m minus 1 plus a sub m minus 2 if n is greater or equal to 2. This is the first 5 terms of the sequence. So here, a0 is the first term. So the first term here is a sub 0, that's 2. Second term is a sub 1, which is 3. For a sub 2, when n is greater or equal to 2, we plug in 2 into this formula. Plug in 2 into this formula. If I plug in 2 for n, I get 2 times a sub. If I plug in 2 for n, 2 minus 1 is 1. I get a sub 1 here. If I plug in 2 for n here, 2 minus 2 is 0. I get a sub 0. A sub 1 is 3. A sub 0 is 2. 2 times 3 plus 2 is 8. A sub 3. I plug in 3 into the formula. I get 2 times a sub 2 plus a sub 1. If I plug in 3 for n, 3 minus 1 is 2. 3 minus 2 is 1. Then a sub 2 is a. A sub 1 is 3. 2 times a, 16. 16 plus 3 is 19. Then for a sub 4, we plug in 4 into the formula. We get 2 times a sub 3 plus a sub 2. A sub 3 is 19. A sub 2 is 8. 2 times 19 is 38. 38 plus 8 is 46. So that's the first 5 terms of the sequence. So the first 5 terms of the sequence is 2, 3, a, 19, 46. Now, in example 1 and 2, for these two formula, if I'm looking for a of 100, a sub 100, I can simply plug in 100 for n and get an answer. For example 1 and 2, if I'm looking for a sub 100, I can plug in 100 divided to n and find the answer. For example 3 and 4, if I try to find a sub 100, I must compute from a1, a2, a3, go all the way down to a sub 100. There's no shortcut to find a sub 100. Same thing for example 4, there's no shortcut to find a sub 100. So for example 1 and 2, this formula doesn't depend on the previous term. It only depends on n. Those are called closed formula. They are called closed formula. Example 1 and 2. These two formulas, they are called closed formula. They are called closed formula. Example 1 and 2, they are called closed formula. For this formula, an doesn't depend on previous term. It only depends on n. So for a sub 100, I can find it directly by plugging 100. They are called closed formula. For example 3 and 4, every term depends on the previous term or the previous terms. Here, in example 3, an depends on the previous term. In example 4, an depends on the previous two terms. Here, if we try to find a sub 100, I need to find every term from 1, 2, 3, 4, 5, go all the way up to a sub 100. There's no shortcut. They are called recursively defined formula. They are called recursively defined formula. They are called recursive defined formula. For example, 3 and 4. Every an depends on the previous term or the previous terms. They are called recursively defined formulas. In general, a recursive defined formula is also called a recurrent relation. Let me give you a formal definition here. A recurrent relation, or sometimes it's called a recursive defined formula. For the sequence an, it's an equation that express a sub n in terms of one or more previous terms. A recursive relation or a recurrent relation or a recursive defined formula for sequence an is an equation that expresses a sub n in terms of one or more previous terms. And the given value of values in the beginning of the sequence are called the initial condition of the recurrent relation. They are called the initial condition of the recurrent relation. For example, in example 3, this is called a recurrent relation. The given value in the beginning of the sequence, this is called the initial condition of this recurrent relation. This is called the initial condition of this recurrent relation. In example 4, this formula here is called the recurrent relation. And the given value 2 and 3, they are called the initial condition of this recurrent relation. So, note, in example 3, a sub 1 equal to 2 is the initial condition. in example 4, a sub 0 equal to 2, and a sub 1 equal to 3. They are the initial condition. In general, if we know the formula of a sequence and try to list the sequence based on the formula, that's easier. However, if we only know the sequence and we try to observe the pattern and find a formula for the sequence, that will be much harder. Let's look at the following examples. Find a general formula for each of the following sequence. First example, observe the sequence 1, a half, a third, a 4, a fifth, and so on. Find a formula for this sequence. This example is easier if you observe these numbers. Number 1 can be rewritten as 1 over 1. And that's 1 over 2, 1 over 3, 1 over 4, 1 over 5. So we can see that for every term, the numerator is the same. The denominator increases. So we have 1 over n, where n is greater or equal to 1. So that's the formula for this sequence. A sub n equal to 1 over n. N is greater or equal to 1. That's the formula for this sequence. Let's look at a different one. A sequence with 3, 7, 11, 15, 19, 23, and so on. Can we see the pattern here? Observe this number here. Observe these numbers. 3 plus 4 will be 7. 7 plus 4 will be 11. 11 plus 4 will be 15. 15 plus 4 will be 19. 19 plus 4 will be 23. So it looks like when we keep adding 4, we can get the next term. So I can write it as A0 equal to 3. Then every term equal to the previous term plus 4. For n is greater or equal to 1. So I can write it as in this form. A0 equal to 3. Then the first one is 3. Every term is the previous term plus 4. 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 15. First one is 3. Every term is the previous term plus 4. So I can write this sequence using a recursive defined formula. Can we find a closed formula for this? Can we find a closed formula for this sequence? For a closed formula, think of this way. Every term, first term is 3 plus 4 once. 11 is 3 plus 4 twice. 15 is 3 plus 4 3 times. 19 is 3 plus 4 4 times, and so on. So it's 3 times 4 plus n. N greater or equal to 0. This is a closed formula. This is a closed formula for this sequence. So when n is 0, 3 plus 4 times 0 is 3. When n is 1, 3 times 4 plus 1 is 7. When n is 2, 3 plus 4 times 2 is 11, and so on. So either form is okay. That's the recurrent relation. That's the recursive defined formula, and that's the closed formula. And this is a special sequence. If we observe this sequence, we can see that the difference between any two consecutive terms is 4. The difference between any two consecutive terms is 4. This sequence has a name. It's called arithmetic sequence. If the difference between any two consecutive terms is the same, the sequence is called arithmetic sequence. This is a special sequence called arithmetic sequence. In a sequence, if the difference between any two consecutive terms is the same everywhere, then the sequence is called an arithmetic sequence. In a sequence, if the difference between any two consecutive terms is the same everywhere, then the sequence is called an arithmetic sequence. In this sequence, the difference between any two consecutive terms is 4. That's why it's called arithmetic sequence. Next example, let's consider a sequence 5, 10, 20, 40, 80, 160, and so on. If we observe the sequence, we can see that the first term of the sequence is 5. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. And 80 times 2 is 160. So if we use the current relation, first term is 5. Then every term else is 2 times the previous term. If n is greater or equal to 1. That's the current relation for the sequence. A0 is 5. And every term is 2 times the previous term. 2 times 5 is 10. 2 times 10 is 20, and so on. That's the current relation. Can we find a closed formula for this sequence? First term is 5. Second term is 5 times 2. Next term is 5 times 2 twice. Next term is 5 times 2 3 times. Then 5 times 2 4 times. 5 times 2 5 times. So in general is 5 times 2 n times. If n is greater or equal to 0. That's the closed formula for this sequence. When n is 0, 5 times 2 to the power 0 is 5. When n is 1, 5 times 2 to the power 1 is 10. When n is 2, 5 times 2 to the power 2 is 20. That's the closed formula for this sequence. And this sequence is also a special sequence. It's called the geometry sequence. This sequence is also a special sequence. It's called geometry sequence. For geometry sequence, let me give you a definition. In a sequence, if the ratio between any two consecutive terms is the same. Then the sequence is called a geometric sequence. If the ratio between any two consecutive terms is the same, then the sequence is called a geometric sequence. So the ratio between the first two terms is 2. Ratio between 10 and 20 is also 2. Ratio between 20 and 40 is also 2. Since the ratio is the same, the ratio between any two consecutive terms is the same everywhere. This is called a geometric sequence. So that's a special sequence, keep it in mind. This is called geometric sequence. Next example. Let's consider the sequence 1, 1, 2, 3, 5, 8, 13, 21, and so on. We try to find a formula for this sequence. Do we see any pattern here? Observe the sequence. Do we see any patterns here? Let's observe carefully here. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. So it looks like the pattern here is every term equal to the sum of the previous two terms. Every term equal to the sum of the previous two terms. Every term equal to the sum of the previous two terms. And the first two terms, they cannot be computed using this formula. So I consider the first two terms, they are initial conditions. A0 equal to 1. A1 equal to 1. And if n is greater or equal to 2, we use this formula. The first two terms cannot be computed using the formula, so we consider the first two terms are initial conditions. Then start from the third term. Every term is the sum of the previous two terms. That's the recurrent relation or the recursive defined formula for this sequence. Is there a closed formula for this sequence? Is there a closed formula for this sequence? The answer is yes, but it's very, very hard to find it right now. In chapter 8, I'll show you a new technique to find the closed formula for this sequence. In chapter 8, I'll show you a new technique to find a closed formula for this sequence. But right now, it's very hard to find it. This sequence is also a special sequence. This is also a special sequence. It's called the Fibonacci sequence. This sequence is also a special sequence. It's called the Fibonacci sequence. Fibonacci sequence, the first two terms are ones. Then for the rest of the terms, it is the sum of the previous two terms. First two terms are ones. Then start from the third term is the sum of the previous two terms. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. This sequence, only this sequence is called Fibonacci sequence. That's a very, very special sequence. This sequence is called the Fibonacci sequence. It can be expressed by the sequence itself or by the formula, by the recursively defined formula. Next example. Consider the sequence 1, 0, 1, 0, 1, 0, and so on. This is not a special sequence, but can we find a formula for this sequence? In this sequence, we can see that first term is the same as the third term. The third term is the same as the fifth term. The second term is the same as the fourth term. And the fourth term is the same as the sixth term. So if we call this A0, A1, A2, A3, A4, A5, we can see that A2 is the same as A0, A4 is the same as A2, A3 is the same as A1, A5 is the same as A3. So I can run the formula as A sub n equal to A sub m minus 2. A sub n equal to A sub m minus 2. A2 equal to A0. A3 equal to A1. A4 equal to A2. A5 equal to A3, and so on. And for this formula, we can only use it to compute A2, A3, A4, A5. We can use it for A0 and A1. So we consider A0 and A1 as initial conditions. A0 equal to 1, A1 equal to 0, AN equal to A sub n minus AN equal to A sub n minus 2 if n is greater than or equal to 2. That's the recursively defined formula for the sequence. That's the recursively defined formula for the sequence. Can we find a closed formula for the sequence? Can we find a closed formula for the sequence? For this sequence, finding a closed formula is not easy, but let's try. Let's try to compare this with some special sequence. Consider a sequence, -1 raised to power n. Consider this special sequence, -1 raised to power n, how it looks like. Consider this special sequence. When n is 0, -1 to the power n is 1. When n is 1, -1 raised to power 1 is -1. When n is 2, -1 raised to power 1 is 1. When n is 3, -1 raised to power 3 is -1. When n is 4, I get 1. When n is 5, I get -1, and so on. Now, this sequence and this sequence looks almost the same, but a little different. Now, if I add 1 to the sequence, what do I get? If I add 1 to the sequence, what do I get? If I make -1 to the power n plus 1, what do I get? If I add 1 to the sequence, 1 plus 1 is 2. -1 plus 1 is 0. 1 plus 1 is 2. -1 plus 1 is 0. So you get 2, 0, 2, 0, and so on. Compare this and this, almost the same. If I divide everything by 2 here, in this sequence, if I divide everything by 2, if I make -1 to the power n plus 1 over 2, I get 1, 0, 1, 0, 1, 0, and so on. That's exactly the same as what we have. So for the closed formula, I can use A sub n equal to -1 to the power n plus 1 over 2 if n is greater than or equal to 0. For this sequence, n starts from 0. So if n is greater or equal to 0, A sub n is -1 to the power n plus 1 over 2. That's the closed formula for this sequence. That's the closed formula for the sequence. Next example. Consider the sequence 7, 77, 777, 7,777. Next one, 77777. Again, this is not a special sequence, but can we find a formula for this sequence? This is not a special sequence. Can we find a formula for this sequence? If we observe the sequence, we can see that here, first term is 7. For the second term, I can take the first term times 10 plus 7. For the second term here, for the second term, I can use the first term times 10 plus 7. And for next term, I can use the previous term times 10 plus 7. 7 times 10 is 70, plus 7 is 77. 77 times 10 is 770, plus 7, I get 777. 777 times 10 is 7,770, plus 7, I get the next term. So We can see that here. Every term is the previous term times 10 plus 7. Every term is the previous term times 10 plus 7. And this formula works for every term except the first term. 77 is first term times 10 plus 7. So every term, this formula works for every term except the first term. So we consider the first term as an initial condition. A sub 0 equal to 7. Then start from n equal to 1. I can use this formula. First term is 7. Every term is 10 times the previous term plus 7. Every term is 10 times the previous term plus 7. 10 times the previous term plus 7. This is the recursively defined formula, or it's called recurrent relation for this sequence. Next, can we find a closed formula for this sequence? Can we find a closed formula for this sequence? Finding a closed formula for this sequence is not easy, but let's compare this sequence to some special sequence. Let's compare this sequence to some special sequence. Let's consider the sequence 10 to the power of n. When n equal to 1, 2, 3, 4, 5, and so on. When n equal to 1, 10 to the power 1 is 10. When n equal to 2, 10 to the power 2 is 100. When n equal to 3, 10 to the power 3 is 1,000. When n equal to 4, I get 10,000. When n equal to 5, I get 100,000. Next, if I subtract each number by 1, I get 9, 99, 999, 9,999, 99,999. Almost the same, right? A little different, almost the same. Now, if I multiply each number by 7 over 9, what do I get? If I multiply each of these numbers by 7 over 9, what do I get? 9 times 7 over 9 is 7. 99 times 7 over 9 is 77. 999 times 7 over 9 is 777. And next one is 7,777. Next one is 77,777, and so on. That looks exactly the same. So the closed formula for this sequence can be written as an equal to 7 over 9 times 10 to the power n minus 1 for n greater or equal to 1. So n is greater or equal to 1. That's the closed formula for this sequence. But the thing is, in this sequence here, if I plug in 1, my A1 is 7, A2 is 77. It doesn't match the index here. So let's rewrite the index. Let's rewrite the sequence. Let's rewrite the index of the sequence. Consider this is A1, this is A2, this is A3, A4, and A5. So in the recurrent relation, I want A1 to be 7. Then every term equal to the previous term times 10 plus 7. If n is greater than or equal to 2, start from the second term, start from a sub 2. I use this formula. So a sub 1 equal to 7, an equal to 10 times the previous term plus 7. If n is greater than or equal to 2, start from the second term, I use the formula. So these two formulas represent the same thing. This is called recursively defined formula. This is called a closed formula. So here, in general, we can see that finding a recursively defined formula is easier. In general, finding a closed formula is harder. But when we're doing computation, using closed formula is easier. Using recursive formula, it may take too much time. For example, if we try to compute a sub 100, we must compute 100 terms. But for this formula, we can get an answer immediately. For the closed formula, we can get a sub 100 immediately. So in general, getting recursively defined formula is easier, but it's hard to use it to do computation. And getting a closed formula is harder, but it's easier to use it to do computation. Next example. Find a closed formula for each of the following recurrent relations. Find a closed formula for each of the following recurrent relations. First example. A sub 0 equal to 4. A sub n equal to n times a sub n minus 1 if n is greater or equal to 1. Find a closed formula for this recurrent relation. So, if we try to find a closed formula, let's write down a few terms. A sub n is n times a sub n minus 1. How about a sub n minus 1? For a sub n minus 1, I plug in n minus 1 for each n. I plug in n minus 1 for each n in the formula. I have m minus 1 times a sub m minus 2. If I plug in m minus 1 here, m minus 1 is m minus 2. Then for a sub m minus 2, I plug in m minus 2 for each n in the formula, plugging m minus 2 for each n. I get m minus 2 times a sub m minus 3. M minus 2 minus 1 is m minus 3, and so on. Next, we try to substitute. I first substitute a sub m minus 1 into this formula. So a sub n equal to n times a sub m minus 1. If I substitute, n stays the same. A sub m minus 1 is m minus 1 times a sub m minus 2. If I substitute, I replace a sub m minus 1 with m minus 1 times a sub m minus 2. That can be rewritten as n times m minus 1 times a sub m minus 2. Next, I replace a sub m minus 2 with n minus 2 times a sub m minus 3. So a sub n equal to n times n minus 1 stays the same. Replace a sub m minus 2 with m minus 2 times a sub m minus 3. That can be rewritten as n times m minus 1 times m minus 2 times a sub m minus 3. Now, let's try to see the pattern here. In general, if we go down to a sub 0, it will be n times m minus 1, m minus 2. The number keep going down until what? If we get a sub 0 here, remember this number is 1 more than this number. This number is 1 more than this index number here. So if the index is 0, the last number must be 1, and the previous one must be 2, the previous one must be 3. So you get n times n sub n minus 1, n minus 2 go down to 3 to 1 times a sub 0. And we know that n times n minus 1 times n minus 2 times 3 to 1, this is n factorial. So an equal to n factorial times a sub 0. And we know that a sub 0 is 4. That's the initial condition. A sub 0 is 4. Plug in 4 for a sub 0. An is 4 times n factorial. For n greater or equal to 0. That's a closed formula for this recurrent relation. That's the closed formula for this recurrent relation. Next example. Let's consider the sequence a sub 0 equal to 6. A sub n equal to 2a sub m minus 1 plus 3 if n is greater than or equal to 1. So a sub 0 is 6. Every term is 2 times the previous term plus 3. We try to find a closed formula for this recurrent relation. Let's first of all write down a few terms for a sub n. A sub n is 2 times a sub m minus 1 plus 3. How about a sub m minus 1? How about the previous term? Here I plug in m minus 1 for each n. I plug in m minus 1 for this n here. I get 2 times a sub m minus 2 plus 3. I replace this m with m minus 1. M minus 1 minus 1 is m minus 2. Next, a sub m minus 2. Here I plug in m minus 2 for this n here. I get 2 times a sub m minus 3 plus 3. If I plug in m minus 2 for n, I get m minus 2 minus 1, which is m minus 3, and so on. Let's write down the first 3 terms first. We may need more terms. Let's substitute. A sub n is 2 times a sub m minus 1 plus 3. I can replace a sub m minus 1 with 2 times a sub m minus 2 plus 3. If I replace it, I have 2 times a sub m minus 2 plus 3 plus 3. Here I replace a sub m minus 1 with 2 times a sub m minus 2 plus 3. Then let's simplify. Here if I distribute 2, I get 2 squared a sub m minus 2 plus 2 times 3 plus 3. Next, I can replace a sub m minus 2 with the next row, 2 times a sub m minus 3 plus 3. Plug in here. So a sub n equal to 2 squared times twice a sub m minus 3 plus 3. And everything else stays the same. Plus 2 times 3 plus 3. These 2 terms stays the same. I replace a sub m minus 2 with this row here. Then if I distribute 2 squared, I get 2 to the power 3 times a sub m minus 3 plus 2 squared times 3. The rest stays the same. 2 times 3 plus 3. Now do we see the pattern here? If we keep going, if the index here become a sub 0, if I have a sub 0 here, that means I have m minus n here. So the exponent here must be n. If the index becomes 0 here, it must be m minus n. So the exponent must be n here. So I get 2 to the power n times a sub 0. How about next term? Next term, the power goes down by 1. Power 3, power 2, power 1. The power goes down by 1. From power n, if the power goes down by 1, it will be 2 to the power of n minus 1. Number 3 stays the same. Next term is 2 to the power of n minus 2 times 3. The power keeps going down until it reaches 2, 1, 0. 2 to the power 2 times 3 plus 2 times 3 plus number 3. 3 is the last term. Now, here I leave the first term the same. For the rest of the terms, they all contain 3. If I factor 3 out, I have 2 to the power of n minus 1 plus 2 to the power of n minus 2 plus 2 squared plus 2 plus 1. And here you can see that this is a geometric series with common ratios 2. This is geometric series with common ratios 2. In calculus class, we know a formula that says 1 plus r squared plus r to the power of n minus 1 plus r to the power of n. The sum of geometric series is the common ratio raised to the highest power plus 1 minus 1 over the common ratio r minus 1. That's the sum for geometric series. And that's a formula we've seen in calculus class. If you don't remember this formula, it's okay. I'll show you the proof later. That's the sum for geometric series. Common ratio to the highest power plus 1 minus 1 over the common ratio minus 1. So let me rewrite this geometric series. 3 stays the same. This is geometric series, so we can use the formula. The common ratio is 2. Highest power is n minus 1, so I do n minus 1 plus 1. Highest power plus 1. Using the highest power plus 1 minus 1 over the common ratio minus 1. That's the sum of the geometric series. Next, let's simplify the geometric series. The denominator is 2 minus 1, which is 1, so I can drop the denominator. What's left here is 2 to the power n. n minus 1 plus 1 is n minus 1. Next, we know that a sub 0 is 6. A sub 0 is 6. I can plug in 6 for a sub 0. I get 6 times 2 to the power n. If I distribute 3, I get 3 times 2 to the power n minus 3. Then I can combine like terms. 6 times 2 to the power n plus 3 times 2 to the power n is 9 times 2 to the power n minus 3. So the cross formula for the current relation is a sub n equal to 9 times 2 to the power n minus 3 if n is greater than or equal to 0. That's the cross formula for this current relation. Next, a sub 0 equal to 2. A sub n equal to a sub n minus 1 plus 2n if n is greater or equal to 1. Find a cross formula for this current relation. So let's write down a few terms first. A sub n is a sub n minus 1 plus 2n. Then for a sub n minus 1, I plug in n minus 1 for each n. So I get a sub n minus 2 plus 2 times n minus 1. Here, I plug in n minus 1 for this n here. n minus 1 minus 1 is n minus 2. Next, for a sub n minus 2, I plug in n minus 2 for each n. I get a sub n minus 3 plus 2 times n minus 2. I plug in n minus 2 for this n here. n minus 2 minus 1 is n minus 3. We may need more terms, but let's write down these 3 terms first. We may need more terms. Next, let's substitute. A sub n is a sub n minus 1 plus 2n. So I first of all replace a sub n minus 1 with the second row. Replace a sub n minus 1 with the second row. an equal to a sub n minus 2 plus 2 times n minus 1. 2n stays the same. It can be rewritten as a sub n minus 2 plus 2 times n minus 1 plus 2n. Next, replace a sub n minus 2 with the next row. So a sub n is a sub n minus 3 plus twice n minus 2. That's a sub n minus 2. The rest stays the same. the rest stays the same. Plus twice m minus 2, twice m minus 1 plus 2n. Next, let's rewrite this formula. It can be rewritten as a sub m minus 3 plus 2 times m minus 2 plus 2 times m minus 1 plus 2n. Now, can we see the pattern? If we see the pattern, we can try to find a better formula. But if we can't see the pattern, we need to plug in more terms. Can we see the pattern here? If a sub m minus 3 goes down to a sub 0, what do we have here? This number, m minus 2, is 1 more than m minus 3. m minus 2 is 1 more than m minus 3. So if the index becomes 0, this number must be 1. And this number is 1 more than m minus 2. m minus 1 is 1 more than m minus 2. So this should be 2 times 2. This number keeps going larger, 1, 2, 3. Eventually it will reach m minus 2, m minus 1 plus 2n. Then for these terms, they all contains 2. For these terms, every term contains a 2. If I factor 2 out, what do we get? We get 1 plus 2 plus m minus 2, m minus 1 plus n. Now, the sum from 1 to n. In calculus class, we know that the sum 1 plus 2 plus 3 go all the way to n is m times m plus 1. That's n times m plus 1 over 2. That's the sum from 1 to n. That's a formula we learned in calculus class. If you don't remember this formula, it's okay. I'll show you the proof later. That's a formula we learned from calculus class. The sum from 1 to n is n times n plus 1 over 2. If you don't remember this, it's okay. I'll show you the proof later. So here, if I compute the sum, the sum from 1 to n is n times m plus 1 over 2. The sum from 1 to n is n times m plus 1 over 2. Then simplify. We know that a0 is 2. These 2 and 2 here can cancel. We get n times m plus 1. Distribute n and combine like terms. This can be rewritten as n squared plus n plus 2. So an equal to n squared plus n plus 2 if n is greater than or equal to 0. The index starts from 0. N is greater than or equal to 0. That's the closed form for this recurrent relation. That's the closed form for this recurrent relation. Next example, a sub 0 equal to 3. A sub n equal to a sub m minus 1 plus 6n squared if n is greater than or equal to 1. Find a closed formula for this recurrent relation. Find a closed formula for this recurrent relation. So let's write down a few terms first. A sub n is a sub m minus 1 plus 6n squared. So a sub m minus 1, if I plug in m minus 1 for n, I get a sub m minus 2 plus 6 times m minus 1 squared. I plug in m minus 1 for each n here. Then next, a sub m minus 2. A sub m minus 2 is a sub m minus 3 plus 6 times m minus 2 squared. We plug in m minus 2 for each n here. M minus 2 minus 1 is m minus 3. And so on. we may need more terms, but let's write down the first 3 terms first. We may need more terms. Now, let's substitute. For a sub n, I get a sub n minus 1 plus 6n squared. If I substitute, I replace a sub n minus 1 within the second row. I have a sub n minus 2 plus 6 times n minus 1 squared plus 6n squared. 6n squared stays the same. I replace a sub n minus 1 within the second row. If I simplify, this can be rewritten as a sub n minus 2 plus 6 times n minus 1 squared plus 6n squared. Next, I can replace a sub n minus 2 within the third row. If I replace a sub n minus 2 within the third row, I get a sub n minus 3 plus 6 times n minus 2 squared. The rest stays the same. Plus 6 times n minus 1 squared plus 6n squared. Now, if I simplify, I get a sub n minus 3 plus 6 times n minus 2 squared plus 6 times n minus 1 squared plus 6n squared. Now, we try to see the pattern. If I keep substituting, when I get a sub 0 here, what do I get here? What's the next term? Observe this number here. We have n minus 3 here, n minus 2 here. n minus 2 is 1 more than n minus 3. n minus 2 is 1 more than n minus 3. So if the index becomes 0, n minus 2 will become 1. And next term, n minus 1 is 1 more than n minus 2. It will be 2 squared. And every turn the number keeps going up. The number keeps going up by 1. Eventually it will reach 6 times n minus 1 squared plus 6n squared. The number keeps going up by 1. The number in the parentheses keep going up by 1. Eventually I get 6 times n minus 1 plus 6n squared. Then for these terms, we can see that they all contain a 6. Every term contains a 6. If I pull out 6, I have 1 squared plus 2 squared plus n minus 1 squared plus n squared. What's the sum of this theory? In calculus class, we know that the sum of 1 squared plus 2 squared plus 3 squared plus n squared, that's n times n plus 1 over 2n plus 1 over 6. That's a formula we seen in calculus class. If you don't remember, it's okay. I'll show you the proof later. So the sum of 1 squared plus 2 squared plus 3 squared plus n squared is n times n plus 1 times 2n plus 1 over 6. If I apply the formula here, I get a0 plus 6 times n plus 1 times 2n plus 1 over 6. Next, let's simplify the formula. a0 here is 3. If I substitute 3 for a0, I get 3 here. 6 and 6 can cancel. I get n times n plus 1 times 2n plus 1. If I distribute and combine like terms, I have n times 2n squared plus n plus 2n plus 1. Then when I combine like terms, I get 2n squared plus 3n plus 1. If I distribute n, I get 2n cubed plus 3n squared plus n. So in general, an equal to 2n cubed plus 3n squared plus n plus 3 if n is greater than or equal to 0. That's the cross formula for this nuclear notation. Next, let me introduce sigma notation Sigma notation is also called summation notation. Sigma notation is also called summation notation. It looks like this. Summation I from n to m. Summation I from m to n of AI. It means that's the initial index, that's the final index. It means we go from am plus 1 plus a sub m plus 2 go all the way up to an. This is called sigma notation. Let's look at some simple example first. Evaluate each of the following expressions. First one, sigma I from 2 to 5, 2i plus 3. So here I varies from 2 to 5, and that means I should be 2, 3, 4, 5. When I is 2, I get 2 times 2 plus 3. When I is 3, I get 2 times 3 plus 3. When I is 4, I get 2 times 4 plus 3. When I is 5, I get 2 times 5 plus 3, which is 7 plus 9 plus 11 plus 13, which is 40. Another example, I from 4 to 6, 2 to the power I. I from 4 to 6, 2 to the power I. When I is 4, I have 2 to the power 4. When I is 5, I have 2 to the power 5. When I is 6, I get 2 to the power 6. So here I is the value from 4 to 6. I represent integers from 4 to 6. I could be 4, 5, 6. Then evaluate the expression. 2 to the power 4 is 16. 2 to the power 5 is 32. 2 to the power 6 is 64. Adding up, that's 112. Next, summation I from -1 to +1. Three I square. I from -1 to +1, 3i square. So I substitute I from -1 to 1, only substitute whole numbers. When I is -1, I get 3 times -1 square. When I is 0, I get 3 times 0 square. When I is 1, I get 3 times 1 square. I is -1, 0, and +1. Substitute I for -1, 0, +1. Then adding up, we have 3 plus 0 plus 3, that's 6. Next, the sum of I from 1 to n of number 1. How do we find the sum here? Here I varies from 1 to n. I could be 1, 2, 3, 4, 5 up to n. How do we find the sum for this expression? When I is 1, I have a constant 1. When I is 2, I also have a constant 1. This expression doesn't depend on I. When I is 1, I get 1. When I is 2, I get 1. When I is 3, I get 1. And when I is n, I also get 1. That means we have 1 plus 1 plus 1 n terms. 1 plus 1 plus 1 n terms together is n. Next, I from 1 to n of I. How about this? I from 1 to n of I. If I substitute 1, what do I get? I have 1. When I is 1, I get 1. When I is 2, I get 2. When I is 1, I get 1. When I is 2, I get 2. When I is 3, I get 3. And so on. When I is n, eventually when I reach n, I have n. How do we find the sum for this expression? Assume this equal to n. I don't know what it is. Assume this equal to s. So assume this equal to s. We try to find the sum s here. Assume equal to s. Then s is 1 plus 2 plus 3 plus n. For another s, if I write it backward, I have n minus 1. If I write it backward, last term is n, second last term is n minus 1, and the third last term is n minus 2, plus the last term is 1. If I add them up, s plus s is 2s. 1 plus n is n plus 1. 2 plus n minus 1 is also n plus 1. 3 plus n minus 2 is also n plus 1. Eventually, the last term, n plus 1 is also n plus 1. How many terms are there? 1 term, 2 terms, 3 terms, up to n. There are n terms. So 2s equal to n times n plus 1. If there are n terms adding together, the sum is n times n plus 1. Then to get s by itself, I divide both sides by 2, and the sum is n times n plus 1 over 2. So this sum is n times n plus 1 over 2. That's the sum of this sequence. Next, sum of I from 0 to n, a times r raised to power I. How do we find the sum for this sequence? How do we find the sum for this sequence? If I substitute 0, I get a. If I substitute 1, I get a times r. If I substitute 2, I get a times r squared. If I substitute 3, I get ar to the power 3. If I substitute n, I get ar to the power n. How do we find the sum for this sequence? Assume the sum is s. We try to find s. S is a plus ar plus ar squared plus plus ar to the power n. If I multiply both sides by r, what do I get? If I multiply both sides by r, I get ar plus ar squared plus ar cubed plus ar to the power n plus 1. And next, if I take rs minus s, if I take the bottom minus the top, what do I get? If I take the bottom minus the top, what do I get? If I take the bottom minus the top, ar and ar get cancelled. Ar squared get cancelled. After ar squared, it should be ar cubed. So ar cubed get cancelled. How about the last term here? in the second row, the term before AR to the n plus 1, the term before must be AR to the power n. That's the term before this. So that's the term before the last term. Then when you subtract, take the bottom minus the top, it get cancelled. Then if I take the bottom minus the top, what's left is a to the power of r plus 1 minus a. Take bottom minus the top. That's the only, a is the only thing left on the top. And that's the only thing left on the bottom. When we subtract, that's what we get. Then if I factor the left side, I have s times r minus 1. If I factor the right side, I have a times r to the n plus 1 minus 1. In order to get s by itself, I divide both sides by r minus 1. So s equal to a times r to the n plus 1 minus 1 over r minus 1. That's the sum. Is this the final answer? Be very, very careful. Be very, very careful. In this expression, when r equal to 1, this expression is undefined. So this expression is true only if r is not 1. When r is not 1, the sum of the sequence is this. But if the sum is 1, if r is 1, how do we find the sum? Or if r is 1, when r is 1, how do we find the sum? When r equal to 1, this summation can be rewritten as a times r to the power, a times 1 to the power I. And we know 1 raised to any power is 1. That's the summation I from 0 to n of a. If I expand this sigma notation, when I is 0, I get a. When I is 1, I get a. When I is 2, I get a. When I is n, I also get a. And from 0 to n, there are n plus 1 terms. From 0 to n, there are n plus 1 terms. So the sum is n plus 1 times a. So the final answer, if r is not 1, the sum is a times r to the power n plus 1 minus 1 over r minus 1. If r equal to 1, then the sum is a times n plus 1. That's your final answer. That's your final answer. Next, let me introduce some property of sigma notation. First property, the sum of I from m to n of ai plus bi equal to the sum I from m to n of ai plus the sum I from m to n of bi. Next, the sum I from m to n of c times ai is c times the sum I from m to n of ai. The proof is very simple. Let me show you here. For the first one, the sum of I from m to n of ai plus bi. If I expand the theory, if I expand the sequence, I can write it as am plus bm. That's my first term. Second term will be am plus 1 plus bm plus 1. Eventually, my last term will be an plus bn. If I expand this sigma notation, that's what I get here. Then I can put all the a's together and put all the b's together. I have am plus 1 plus the last one is an. Then I can put all the b's together. I have bm plus 1 plus the last term bn. Then I write this back in the first part back in sigma notation. I have the sum of I from m to n of ai. I write the second part in sigma notation. I have the sum of I from m to n of bi. That's the first one. The second one, the sum of I from m to n of c times ai. If I expand the sigma notation, I have ca sub m plus ca sub m plus 1 plus the last term can. For each term here, c is a common factor. If I pull out c, I have am plus 1 plus an. Then if I put it back in sigma notation, I have c times the summation I from m to n of ai. That's the proof. Keep this property in mind. Next, find a closed form for the sigma notation I from 1 to n of I squared. A closed form means an expression without sigma notation. A closed form means an expression without sigma notation. From your calculus class, probably you remember this is n times n plus 1 over 2n plus 1 over 6. From your calculus class, probably you know this. But today I'll show you how to find this formula. From your calculus class, probably you know this formula. Today I'll show you how to derive the formula. Today I'll show you how to derive this formula. So, step by step. First of all, before I compute this, let's compute a special theory first. Let's compute a special sigma notation first. How do we compute this sum? I from 1 to n of I plus 1 cube minus I cube. How do we compute the sum for this theory? The sum of sequence is called theory. How do we compute the sum for this theory? So to compute the sum, I first of all plug in I equal to 1, I equal to 2, I equal to 3, up to I equal to n, then add them up. Now here, to make the problem a little easier, I substitute backward. I substitute I equal to n first, then I substitute I equal to n plus 1, n minus 1, I equal to n minus 2, eventually go down to I equal to 3, I equal to 2, I equal to 1. So I write it backward. I substitute I from 1 to n, but I write it backward. I from I equal to n, I equal to n minus 1, I equal to n minus 2. Go all the way down to I equal to 3, I equal to 2, I equal to 1. I substitute backward. So what do I get here? If I substitute n, I have n plus 1 cube minus n cube. If I substitute n minus 1, I have n minus 1 plus 1, which is n. I have n cube minus n minus 1 cube. If I substitute n minus 2, I have n minus 1 cube minus n minus 2 cube. Let me put 3 to 1 here. If I substitute n equal to 3, I have 4 cube minus 3 cube. If I substitute I equal to 2, I have 3 cube minus 2 cube. If I substitute I equal to 1, I have 2 cube minus 1 cube. Then let's simplify this expression. Negative n minus 3 and positive n minus 3 get cancelled. Negative n minus 1 cube and positive n minus 1 cube get cancelled. Negative n minus 2 cube will be cancelled by the next term. Positive 2, negative 2 will be cancelled. Positive 3, negative 3 will be cancelled. And positive 4 will be cancelled by the previous term. So what's left is n minus 1 cube minus 1 cube. That can be rewrite as expand the perfect cube. I have n cube plus 3n squared plus 3n plus 1 minus 1. And cancel positive 1 minus 1, I get n cube plus 3n squared plus 3n. So keep this formula in mind. This summation I plus 1 cube minus I cube equal to n cube plus 3n squared plus 3n. Now let's simplify the left side in a different way. On the left side, if I expand a perfect cube, I have I cube plus 3i squared plus 3i plus 1 minus I cube. Leave the right side the same. On the left side, I cancel I cube. I have the sum I from 1 to n of 3i squared plus 3i plus 1 equal to n cube plus 3n squared plus 3n. Then, by the previous property, we're allowed to split this into 3 summations. We have sum of I from 1 to n of 3i squared, sum from 1 to n of 3i, plus the sum of I from 1 to n of 1. Then I can pull out the coefficient. Pull out 3. I have 3 sum of I from 1 to n of I squared. Pull out 3, I get sum of I from 1 to n of I plus the sum of I from 1 to n of 1 equal to n cubed plus 3n squared plus 3n. Then we know the sum of 1. From the previous example, the sum of 1 is n. Sum of I from 1 to n is n times n plus 1 over 2. And the sum of 1 is n. Sum of I from 1 to n, that's n times n plus 1 over 2. And the sum of I squared, that's what we are looking for. The sum of I squared, that's what we are looking for. Let's call this sum equal to s. We are looking for this s. I don't know what it is. We are looking for s. That equal to n cubed plus 3n squared plus 3n. This is the equation of n and s. This is the equation of n and s. I can solve this equation for s and write s in terms of n. So I can, first of all, to make it easier, I multiply both sides by 2, which I make 6s plus 3n times n plus 1 plus 2n equal to 2n cubed plus 6n squared plus 6n. Then I try to distribute 3n and combine like terms. Distribute 3n, I have 6s plus 3n squared plus 3n plus 2n equal to 2n cubed plus 6n squared plus 6n. Then if I combine like terms, I have 6s plus 3n squared plus 5n equal to 2n cubed plus 6n squared plus 6n. Then subtract 3n squared from both sides, subtract 3n squared from both sides, subtract 5n from both sides. I have 6s equal to 2n cubed plus 3n squared plus n. Then I can try to factor the right side. If I factor, I can first of all pull out n. I have 2n squared plus 3n plus 1. Then keep factoring. I have n times 2n squared can be rewritten as n times 2n. I try to factor 1, make an outer and inner together to be 3n. For number 1, the only possibility is positive 1, positive 1. Check the outer and inner. Outer is 1n, inner is 2n, together is 3n. Then to get s by itself, I divide both sides by 6. So that's the answer. So keep this formula in mind. I from 1 to n of I squared equal to s. S is n times n plus 1 times 2n plus 1 over 6. Keep this formula in mind. Next, find a closed form for the summation I from 1 to n of I cubed. From your calculus class, probably you know the answer. That's n squared times n plus 1 squared over 4. That's the answer we know from our calculus class. Today I will show you how to get the answer. We find the answer using a very similar technique. We find the answer by using a very similar technique. We first of all compute the sum I from 1 to n of I plus 1 to the power 4 minus I to the power 4. So I first of all expand this sigma notation and write it backward. Right, I from n, I equal to n, I equal to n minus 1, I equal to n minus 2, and go down to I equal to 3, I equal to 2, and I equal to 1. Write it backward. Expand sigma notation, write it backward. So when I equal to n, I have n plus 1 to the power 4 minus n to the power 4 plus n to the power 4 minus n minus 1 to the power 4 plus n minus 1 to the power 4 minus n minus 2 to the power 4 plus when I is 3, I have 4 to the power 4 minus 3 to the power 4. When I is 2, I have 3 to the power 4 minus 2 to the power 4. When I is 1, I have 2 to the power 4 minus 1 to the power 4. That's when I equal to 3, I equal to 2, I equal to 1. Usually we write it in increasing order. We write I equal to 1, I equal to 2, I equal to 3 in this order. But here, to make it easier, I write it backward. I write last term first. N, I equal to n, I equal to n minus 1, I equal to n minus 2. Then go down to I equal to 3, I equal to 2, I equal to 1. Then if I simplify, negative n to the power 4 and positive n to the power 4 can cancel. Negative n minus 1 to the power 4 and positive n minus 1 to the power 4 can cancel. Negative n minus 2 to the power 4 will cancel by the next term. And on the other side, I cancel backward. Positive 2 to the power 4 and negative 2 to the power 4 can cancel. Positive 3 to the power 4 and negative 3 to the power 4 can cancel. And 4 to the power 4 will be cancelled by the previous term. What's left is n plus 1 to the power 4 minus 1 to the power 4. That's the summation I from 1 to n I plus 1 to the power 4 minus I to the power 4. Then simplify the right side. We can simplify both sides at the same time. Let's simplify both sides at the same time. Expand I plus 1 to the power 4. Expand I plus 1 to the power 4. I have I to the power 4 plus 4i cubed plus 6i squared plus 4i plus 1. Expand I plus 1 to the power 4 minus I to the power 4. On the right side, expand this. Expand n plus 1 to the power 4, which is very similar. N to the power 4 plus 4n to the power 3 plus 6n squared plus 6n plus 1 minus 1 to the power 4 is 1. Then on the left side, I cancel I to the power 4. I have a summation I from 1 to n 4i cubed plus 6i squared plus 4i minus 1. On the right side, I cancel positive 1 and negative 1. I get n to the power 4 plus 4n cubed plus 6n squared plus 6n. Positive 1, negative 1 get cancelled. That should be 4n, sorry. Then on the left side, I can split the terms. I have summation I from 1 to n of 4i cubed. That should be plus 1, sorry. plus summation I from 1 to n of 6i squared, summation I from 1 to n of 4i plus summation I from 1 to n of number 1. That equal to n to the power 4 plus 4n cubed plus 6n squared plus 4n. On the left side, I can pull out the coefficient, make 4 times summation I from 1 to n of I cubed, pull out 6, I from 1 to n of I squared, pull out 4, I from 1 to n of I, and last one is I from 1 to n of 1, equal to n to the power 4 plus 4n cubed plus 6n squared plus 4n. Then let's use the formula for the summation of 1. The sum of 1, that's n. The summation of I is n times n plus 1 over 2. The sum of I squared we just found. The sum of I squared we just found. That's n times n plus 1 times 2n plus 1 over 6. That's the sum of I squared. We don't know the sum of I cubed. That's what we are looking for. Let's assume the sum of I cubed equal to s. We solve the equation for s. So it's 4 times s plus this. 4 times s plus 6 times the sum of I squared plus 4 times the sum of I plus the sum of 1 equal to n to the power 4 plus 4n cubed plus 6n squared plus 4n. Then simplify left side. We have 4s plus, I cancel 6 from top and the bottom, multiply n times n plus 1 times 2n plus 1. If you multiply correctly, it should be 2n cubed plus 3n squared plus n. 4 divided by 2 is 2. Distribute 2n, we have 2n squared plus 2n plus the last n equal to n to the power 4 plus 4n cubed plus 6n squared plus 4n. Then I can combine right term on the left side first. I get 2n to the power 3 plus 5n squared plus 4n equal to n to the power 4 plus 4n cubed plus 6n squared plus 4n. Then subtract 2n cubed from both sides, subtract 5n squared from both sides, subtract 4n from both sides. I get 4s by itself. I have n to the power 4 plus 2n cubed plus n squared. 4n get cancelled. Then I can factor, pull out n squared. I have n squared plus 2n plus 1. Let me carry everything over. 4s equal to n squared times n squared plus 2n plus 1. If you factor n squared plus 2n plus 1, that's a perfect square trinomial. That's n plus 1 squared. Then divide both sides by 4. I get n squared plus n plus 1 squared over 4. That's the formula we see in our calculus class. So keep this formula in mind. The sum of I from 1 to n of I cubed equal to n squared n plus 1 squared over 4. So That's important. That's a formula which is very important for your calculus class. Those are the formula which we learned today. You can pause the video and copy the formulas. Next, I will show you how to use these formulas. Evaluate each of the following expressions. I from 1 to 100, 4i squared. I from 1 to 100 of 4i squared. I can first of all pull out constant 4. I from 1 to 100 of I squared. This is use the formula that sum of I from 1 to n is sum from 1 to n of I squared is n times n plus 1 times 2n plus 1. So plotting 100 for n, we have 100 times 100 plus 1 times 2 times 100 plus 1 over 6. Then use my calculator. I guess a huge number, 1,353,400. Next, find the sum I from 1 to 50. Six I cube minus 2i. So I first of all split the terms first. I from 1 to 50 of 6i cube minus the sum I from 1 to 50 of 2i. Then I can pull out constant. Pull out 6, pull out 2. 6, the sum of I from 1 to 50 of I cube minus 2 times the sum I from 1 to 50 of I. Then use the formula. The sum of I cube, the sum of I cube is n squared times n plus 1 squared over 4. The sum of I cube is n squared times n plus 1 squared over 4. And if you match the formula here, this 50 represents n. So I plug in 50 for n. I have 50 squared times 50 plus 1 squared over 4 minus 2i. I, the formula of I is n times n plus 1 over 2, and this I stands for 50. We plug in 50 for this n. Plug in 50 for this n. I have 50 times 50 plus 1 over 2. Then use my calculator. I get 9,751,200. Next, how do we find the sum I from 50 to 100 of I squared? I from 50 to 100 of I squared. What should we do? This formula, for this formula, they all start from 1. For the first 4 formula, they all start from 1. And we have I squared. For the formula of I squared, index start from 1. What should we do here? I from 50 to 100. So what I can do is, I first of all compute the sum from 1 to 100. I first of all compute the sum from 1 to 100. but from 1 to 100 that's too much. Then I remove the sum of the terms from 1 to 49. I first of all compute the sum from 1 to go up to, all the way up to 100. Then I have 49, 50, somewhere in the middle, 50, 51. I first of all compute the sum from 1 to 100. Then I subtract the sum from 1 to 49. What's left is the sum from 51 to 100. What's left is the sum for I from 50 to 100. I first of all compute the sum from I equal to 1 to I equal to 100. Then I subtract the sum from I equal to 1 to I equal to 49. What's left is the sum for I from 50 to 100. That's what's left. So that's what we want. I first of all compute the sum from 1 to 100 first. It's 100 times 100 plus 1 times 2 times 100 plus 1 over 6. I substitute 100 in this formula for each n. I substitute 100 for each n in this formula. Next, I find the sum for I from 1 to 49. Use the same formula, I substitute 49 for each n. I substitute 49 for each n. I have 49 times 49 plus 1, 2 times 49 plus 1 over 6. Then I'll use my calculator. I get 297,925. Next, how do we compute double summations? I from 2 to 4, j from 1 to 6, I plus j. How do you compute double summation? If there are double summation, we compute the inner one first. If there are double summation, we compute the inner one first. So I leave the outer summation the same. Compute the inner one first. Take j from 1 to 6. When j is 1, I got I plus 1. When j is 2, I got I plus 2. When j is 3, I get I plus 3. When j is 4, I get I plus 4. When j is 5, I get I plus 5. When j is 6, I get I plus 6. Then simplify. Then simplify completely. I have 6 i's. 1 plus 2 plus 3 plus 4 plus 5 plus 6, that's 21. Then evaluate for I take value from 2 to 4. I have 6 times 2 plus 21, 6 times 3 plus 21, 6 times 4 plus 21, which is 33 plus 39 plus 45. Adding up, I get 117. Next example, I from 3 to 5, j from 2 to I, 2i minus j. Usually, when we see multiple summation, we start from the inner summation first. But this is a special case. The inner summation depends on the outer summation. The inner summation depends on the outer summation. In this situation, you see that inner summation contains I. I depends on the outer summation. So we can start from the inner. If I start from inner, j goes from 2 to I. We don't know what I is. I may be 3, maybe 4, maybe 5. We don't know what I is. So I can't start from inner. I must start from the outer summation first. Start from outer summation. Take I from 3, 4, and 5. Do the outer summation first. When I is 3, I have j from 2 to 3. When I is 3, I have j from 2 to 3. 2 times 3 is 6. 6 minus j. That's when I equal to 3. When I equal to 4, I have j from 2 to 4. 2 times 4 is a minus j. When I is 5, I substitute 5 for each I. I have j from 2 to 5. 2 times 5 is 10. 10 minus j. Then evaluate each one individually. Now we have 3 summation. Evaluate each one individually. When j is 2, I have 6 minus 2, which is 4. When j is 3, I have 6 minus 3, which is 3. Next, when j is 2, I have a minus 2, that's 6. When j is 3, a minus 3 is 5. When j is 4, a minus 4 is 4. Next, when j is 2, 10 minus 2 is a. When j is 3, 10 minus 3 is 7. When j is 4, 10 minus 4 is 6. When j is 5, 10 minus 5 is 5. Then adding up, I have 7 plus 15 plus 26. Adding up, 22 plus 26 is 48. Next, I from 1 to 40, j from 1 to I plus j. What should we do here? If I start from the inner loop, I have j from 1 to I. I don't know what I is, so I don't know how many terms I should add up here. But if I start from the outer loop, I goes from 1 to 40. There are too many terms. There are 40 terms. We need to solve 40 summation individually. That's almost impossible. So in this situation, we need to use the formulas. Keep the formula in mind. We need to use it here. If we plan to use the formula, we start from the inner loop. This can be rewritten as summation j from 1 to I of I plus summation j from 1 to I of j. Keep an outer summation the same. For inner summation, since index is j, I treat I as a constant. When the index is j, I treat I as a constant, so I can pull constant outside. If I pull out constant, what's left is number 1. Leave the second one the same. The summation of 1 is what? I from 1 to n of 1. Summation of 1 equal to n. That equal to the upper limit. Summation of 1 equal to n equal to the upper limit. Here upper limit is I. So that equal to I. How about summation of j? Summation index is j. What's summation of j? When index is I, summation of I is n times n plus 1 over 2. When the index is I, the sum of I from 1 to n is n times n plus 1 over 2. Here index is j. the sum of j from 1 to I here. If you match the formula, this I represent n here. So I substitute I for each n. If I substitute I for each n, I have I times I plus 1 over 2. Then simplify this. This can be rewritten as I squared plus I squared plus I over 2. Adding up, it can be rewritten as 3I squared plus I over 2. Then I can pull out half as a constant. I can treat this 2 as a half. Pull out half as a constant multiple. I have 3I squared plus I. Then it can be rewritten as summation I from 1 to 40 of 3I squared plus summation I from 1 to 40 of I. Then I can pull out 3 again. I get half. 3 times summation I from 1 to 40 of I squared plus summation I from 1 to 40 of I. That's half of 3 times summation of I squared. If you remember the formula, I from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. So here, my upper limit is 40. I plug in 40 for each n. I have 40 times 40 plus 1 times 2 times 40 plus 1 over 6. Summation of I from 1 to 40. I plug in 40 for this n here. I get 40 times 40 plus 1 over 2. Then I use my calculator. I get 33,620.